So in the preceding section, we saw that the general solution of a homogeneous linear nth order differential equation was the linear combination of the solutions from its fundamental set. So here, y1 through yn are fundamental solutions from the fundamental set, meaning that they are all linearly independent, and there are exactly n of them, where n is the order of this differential equation. So what we're going to do in this section is put our attention specifically on second order homogeneous linear differential equations, which means that their solution will have merely a constant times some function plus another constant times another function. So they'll just have two elements in the fundamental set. And our particular attention will be on the situation where if we know one of the solutions, we can use a method called reduction of order to determine the other solution. Okay, so again, if we know one of the solutions, we're going to use this process called reduction of order to deduce the other solution. All right, well, let's describe the situation we're dealing with and come up with a technique for finding that second unknown function. So let's consider. Now we're going to write this guy in standard form, meaning that the highest order derivative has a coefficient of 1. So if you're working with a differential equation that doesn't have that, let's just divide everything by that coefficient, like you would do when solving a linear first order equation. And we'll assume we're working over some interval where p of x and q of x are continuous. Okay, so let's suppose that we have a known solution. We'll call it y1. And we will also stipulate that y1 is not equal to 0. So first of all, we know 0 is a solution, which is why we're saying y1 is not that one particularly. y1 is more interesting than 0, so it actually has stuff involved. And we also know that because we know y1 is a solution, that every multiple of y1 is a solution, right? We know that as a corollary from the superposition theorem that we saw in the last class. So what we're looking for is a second solution, and that second solution needs to be linearly independent from the first one. So in other words, what does that mean? Well, if we set y2 equal to u times y1, then we know that u is not equal to a constant. So in other words, u is some function involving x that when multiplied by y1 will give you y2. All right, so what we're going to do is we're going to make the assumption that we do have such a solution y2, and that it's of the form u times y1, where u is just not a constant. And what we're going to do is take some derivatives and plug those into the original differential equation and see what we can work with. So let's let y equal u times y1. And this y is going to be our new second solution. So we'll call it y2, but we'll do that at the end so we don't have to write little 2's everywhere. So let's take a derivative. Y prime is going to require the product rule, and it requires the product rule because u is not a constant. So this is going to be the derivative of u times y1 plus u times the derivative of y1. All right, we will also need a second derivative. So again, we'll need the product rule and we'll need it twice. So we have derivative of u prime times y1 plus u prime times the derivative of y1 plus, now the product rule applied to this other term, derivative of u times y1 prime plus u times the second derivative of y1. All right, well, this cleans up a little bit. We can say this is u double prime y1 plus 2u prime y prime, or y1 prime, plus u y1 double prime. Okay, well, what we want to do is take these three pieces and insert them into the differential equation. So the original differential equation was y double prime plus p of x times y prime. Let's just write p times y prime, just to make the notation easier to work with, and q times y, and this is equal to 0. So now let's replace each of those y primes and y double primes and so on with these big u, y1 thingies that we have over here. So y double prime is u double prime y1 plus 2u prime y1 prime plus u times y1 double prime. Then we have p times y prime, and y prime is u prime y1 plus u times y1 prime. And then finally, we're going to add q times y. And y is u times y1. Okay, and this is all equal to 0. Now, this is p and q multiplied by these things. It's not p of that. It's not like we're plugging those into the function p. So just want to be clear. Okay, now this is a lovely mess. Well, let's be clear about what we're working with here. This is a differential equation where we're solving for the unknown function u. Remember, y1's not an unknown function. That's actually a known solution. So y1 is just an actual function that's in here. And p and q are actual functions. They're just expressions involving x, as y1 is an expression involving x. So the only thing that's unknown is, of course, u. And we can solve this differential equation for u. And once we've done that, knowing what u is and knowing what y1 is, of course, we'll be able to determine that other missing solution, which is y, or y2, is equal to u times y1. So we're going to solve this differential equation for the unknown function u. And in order to do that, let's arrange the terms by the order of the derivative of u. So let's first distribute everything out so we have a bunch of individual terms, and then we can arrange by derivative of u. So we only have the one term here with a u double prime, so that's y1 times u double prime. And I'm just going to underline the terms that are handled, so we've handled that one. Now, what are all the terms with a u prime? So this guy and this one, those both have u primes. So we can see this is 2y1 prime plus p y1, and that's the coefficient of u prime. And finally, the remaining terms here just have u to the 0th derivative. So that would be y1 double prime plus p y1 prime plus q y1. That's all multiplied by u, and that's all equal to 0. Okay, so here's where the magic happens. This entire coefficient of u here is equal to 0. And why is that? Because that's the original differential equation with y replaced by the known solution y1. So we know that since y1 is a solution to the original differential equation, well, it satisfies it, which means this whole thing is 0. Okay, well that seemed very magical. So what do we have? We've got y1 times u double prime plus 2y1 prime plus py1 times u prime is simply equal to 0. Now this is still a second order homogeneous linear differential equation. However, we can now change it to a first order by making a quick substitution, and this is where the term reduction of order comes from. So what we're going to do is we're simply going to let w equal u prime. And therefore, w prime is u double prime. All right, well, let's see what happens. So our differential equation becomes y1 times w prime plus 2y1 prime plus py1 times w is equal to 0. This is now a first order linear differential equation. We know how to solve those. So let's write it in standard form by dividing by y1. We're allowed to do that because y1 is not equal to 0. So we would get w prime plus this thing, which would be 2y1 prime over y1 plus p times w is equal to 0. All right, well, we will solve this as a first order linear differential equation, which means we're going to need an integrating factor. So we're going to let mu be e to the antiderivative of all of that thing. So that would be 2y1 prime over y1 plus p dx or dt, or we never actually talked about what the independent variable is, but we'll just go with x in this case. So, okay, well, let's split this integral. All right, let's start with this one right here. So we can actually do a u substitution on this guy. If you let u equal y1, then your du is y1 prime dx. Hey, we got that right there. So that little integral there is simply 2 over u du, which integrates to 2 times ln of absolute value of u plus some constant, which would integrate to 2 times ln of absolute value of y1 plus some constant. Okay. And of course, we don't need the constant here since this is going to be part of an integrating factor. And we don't even need the absolute value because we can just move the 2 inside the log and square the y1. So this becomes e to the 2 ln of y1 plus the integral of p dx. And remember, p is a function of x, so you can't just say, oh, that's p times x. It's not. We don't know what p is, and we will never know unless we're doing a specific example with a specific p, which of course we're going to be doing after working out this method. So, okay, well, what do we have? This just becomes y1 squared multiplied by e to the antiderivative of p dx. Let's even write that as p of x dx. So we really don't forget that that is a function that needs to be eventually integrated. All right, well, as a linear differential equation, we can get to its form. So that is the integrating factor times the unknown function, which is w. That's equal to antiderivative of the integrating factor times the right-hand side. That's 0. So what we have is mu times w. Okay, so mu, which is y1 squared, e to the antiderivative of px dx, times our unknown function w, is equal to the antiderivative of 0, which is a constant. Let's call it C1. Okay, so solving for W, we get that W is C1 times e to the negative integral of p of x dx, and that's all divided by y1 squared. All right, but recall that W is equal to u prime. So this means that u prime is equal to all of this nonsense. All right, so integrating both sides will give us our u once and for all. So u is going to be the antiderivative of all of that. Let's factor that constant out. So we have the antiderivative of e to the negative antiderivative of p of x dx, all divided by y1 squared dx. So yes, it's an integral containing an expression with another integral in it. That's super fun. Now remember, we're just looking for one linearly independent solution. So we can actually specifically set this constant equal to 1 for now. Because it doesn't matter. When we put together our final general solution, we know there'd be another constant going in front of this thing. So that's where it would come back and be useful to us. But for this purpose, we're just going to set it equal to 1. So we're going to ignore that constant. But also recall that y, which was really our y2, was defined to be u times y1. This means that u is equal to y2 over y1. And we finally have the form of our second solution. Because if we multiply both sides by y1, then we're going to get y1 times the integral of e to the negative p of x dx, all divided by y1 squared dx. And that formula I recommend writing down so that it's accessible to you. And we're going to just use it to work through the next few examples of finding that second solution. But this is how we would do it. You've got one solution, say y1. You just apply this formula and you're going to get that second solution, y2. And once you have both of those, we know that that's all we need for the general solution of a second order homogeneous linear differential equation. All right, so here we have a second order homogeneous linear differential equation, and we are provided with one solution to it. And we're going to now use reduction of order to find a second independent solution. And once we have both of them, we know we're done, because second order will only have the two. And we can put them together to form the general solution. So of course, this independent is important, so we can't just say, oh, here's another solution, because it is, but it's not linearly independent from the e to the x. In fact, we already looked at this differential equation in the last section, and we're provided with both e to the x and e to the negative x. So I thought this was a good example to start with here, because we know that the other independent solution is supposed to be e to the negative x. All right, but let's arrive there. It's always nice to get there. So let's take a look at the pieces of our second order homogeneous linear differential equation. So let's note here that our p of x is actually 0. That's the coefficient of the y prime, and our q of x is -1. And you could see this if you wrote this, say, as y double prime plus 0 times y prime minus y equals 0. All right, well, what we're going to do is we're going to use the formula that we uncovered in the last section, which looks like this. y1 times the integral of e to the negative integral itself of px dx, all divided by y1 squared dx. So note that we were given y1, which is e to the x. Okay, so our y will be e to the x times the integral of e to the negative integral of p of x. P of x is just 0. And this is all over y1 squared. So that would be e to the x, which itself is squared. So we definitely have some cleanup to do. And I hope it's not news to you that this e to the x outside the integral in no way can interact with the e to the x down here. This e to the x outside the integral is just going to have to patiently wait for us to work out the integral before it can start interacting with things. Well, we know that the integral of 0 dx is just a constant. So we could say this is e to a constant. But remember, this particular form comes from the integrating factor for solving that first order linear equation that emerged partway through the process. So as the integrating factor, we can choose any constant we want. And why don't we just call that 0? So we'll just let c equal 0 there. So we're actually just saying that this entire integral evaluates to 0. So we have e to the 0, or e to the negative 0, which evaluates to 1. So that numerator is simply 1, and the denominator will be e to the 2x. Okay, well this is e to the x times antiderivative of e to the negative 2x. And we can work that out. So this is e to the x times negative 1/2 e to the negative 2x. Again, there is a constant that's generated, but we're just deferring it till later. We're only at the moment looking for a fundamental solution. Then when we form the general solution, we're going to place the constants in front of those because we know that's the form of the final answer. So what do we get here? We get negative 1/2 e to the negative x. Even this negative 1/2 coefficient we can throw away. So we can just let y2 be e to the negative x. And that is our second solution. So therefore, the general solution is y equals c1 times y1 plus c2 times y2, which is c1 times e to the x plus c2 times e to the negative x. And now you can see why we are rejecting those constants earlier, because we're just going to apply them right here, and there's the form of our final answer. So that negative 1/2, totally unnecessary, right? We just threw that away. But even this constant of integration way up here, let's say we insisted on it, I don't know, let's just call it c, then this guy here would be this thing plus c e to the x, and again, that plus c e to the x, once you get down to the final general solution, can just get pushed in with this c1 e to the x. So for that reason, we ignore that constant. It's kind of like we're slowly erasing all the good habits you picked up in Calc 2. Of course, those are good habits, and you should keep those good habits. It's just in this context, we have a license to specifically choose 0 and 1 constants as needed, because we know we're going to put the proper constants in later. Okay, here, very similar situation. We are given a fundamental solution, y equals x squared, to this differential equation. And we're told to find a second independent solution and then form the general solution. Okay, very good. So first thing we should do is rewrite the differential equation in standard form. So for standard form, we just want this essentially written as it is, but we want the coefficient of the highest order derivative to be 1. So we're going to just divide everything by x squared. So we have y double prime plus 2 over x times y prime minus 6 over x squared, y is equal to 0. Okay, so we can see our p of x is 2 over x, and our q of x is negative 6 over x squared. Okay, so now we're going to let y equal y1 times the integral of e to the negative this thing divided by y1 squared dx. So this is equal to, well, y1 is x squared, right? That was the given solution. Integral of e to the negative integral of p of x being 2 over x dx. And this is all over y1 squared. So that would be x to the 4th. Okay, so let's work out this integrating factor here in the numerator. So we can see that this is going to be e raised to the negative 2 ln x. And in fact, we can simply write that as x to the negative 2. So this is x squared, x to the negative 2 over x to the 4 dx. All right, so this isn't going to be too bad as an integral because it's just integrating x to the negative 6 dx. Well, that integrates to x to the negative 5 divided by negative 5. And again, we're not worrying about the constant. So this evaluates to negative 1/5 x to the negative 3. All right, so what we're going to do is throw away the negative 1/5, and we're going to assign y2 to be x to the negative 3, or 1 over x cubed. So this is the other fundamental solution. To be clear, a fundamental solution does not have to have a coefficient of 1. For instance, we could have assigned negative 1/5 x to the negative 3 to be the second fundamental solution. It's just unnecessary to have a specific constant, right? Because our general solution is now going to look like this. Y is equal to c1y1 plus c2y2. So that would be c1 x squared plus c2 over x cubed. And of course, you are always encouraged to take this general solution and see if it satisfies the original differential equation, as it will.